Hello, and welcome to Empowered Learning. This video will be the first of two videos about the convolution operation and its role in solving ordinary differential equations. So this first video will basically talk about the binary operation that we know as convolution itself, doing a few examples of that and stating some of its important properties. The second video, we will see how we can use this binary operation called convolution along with using Laplace transforms to be able to solve ordinary differential equations, specifically ordinary differential equations that have zero initial conditions, meaning that if we have, let's say, a second order differential equation, then we'll have two initial conditions where both of those initial conditions will end up equaling zero. We do have strategies for dealing with initial value problems that are ordinary differential equations where at least one of the initial conditions is not zero. We do have that, and I will state that, and that will also be stated in the second video. So let's get started. So the primary goal of a course in differential equations, which is probably what you're taking if you're looking at this video, is to arm you with the tools or techniques to be able to solve ordinary differential equations of various types. So hopefully you've seen at this point in your study of solving ordinary differential equations that we can use several different methods to solve the same type of equation. We see that some of the methods that are used to solve an ordinary differential equation are much quicker than other methods all the time. So in other words, we have some methods that if we do them for certain types of differential equations, we know that they always work and they're nice and quick. Okay. So other ordinary differential equations can be solved by different methods more efficiently, depending upon how complex the functions that appear in the equation tend to be. So for example, if we took this second order differential equation, non-homogeneous differential equation here, we know that we could solve it by variation of parameters. However, if we tried to solve this by, let's say, method of undetermined coefficients, really it would be almost impossible to do it because the method of undetermined coefficients doesn't even work for this type of function here, okay? But you could try to rewrite secant as a power series and of course express it as an infinite polynomial and then deal with it that way. But again, one of the characteristics of this particular function is we have to have a finite number. We have to be able to express the function as a finite number of derivatives. So that means for like sine and cosine, these functions, if we were to take successive derivatives of it, we would just see that we end up getting either sine or cosine for either one of these. But of course, for let's say tangent, secant, cosecant, that doesn't work. So trying to do this method here would at best be pretty hard and probably at worst not even possible. So for Laplace transforms, we could solve it this way as well. But again, I would have to be able to take the Laplace transform of this, okay? And so that would be not impossible, but kind of difficult to do. And, you know, we really want to take the easiest road that we can to get to some of the answers to some of these ODEs. So that's why for a situation like this, variation of parameters would be probably the preferred method. Now, the point that I'm getting at here is that the whole point of us learning about convolution is that we eventually want to use this new operation that we're going to come up with to be able to solve ordinary differential equations and make our lives a little bit easier, okay? Now, let's note that in the study of Laplace transforms and their use in solving ordinary differential equations, we saw, and I'm saying this because if you've watched my videos on Laplace transform, you saw that we actually worked out all three of these problems, okay? I actually had more, but I worked on these three specifically. And I know that these last two here got very, 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 very long, okay, if we were doing it just by pure Laplace transforms. So we know here that we saw that equations like these, they took a major effort to solve in just using the Laplace transform. But these linear non-homogeneous equations would also take some effort if we did it by method of undetermined coefficients, okay? So with having to put so much effort to solve these types of equations using either the aforementioned methods, the internal question that you probably ask yourself is the following. There has to be a better, faster, more efficient way than we could possibly solve some of these ODEs that have more complex functions in them. So basically speaking, there has to be a better way to do this. And hopefully it's not as long. Well, fortunately, there is a technique that we can use that would possibly, and I emphasize the word possibly because sometimes what we're about to learn is actually more difficult than some of the other things that we want to do. But sometimes possibly accomplish this goal in some situations, okay? Now, what I want us to do to kind of get the idea or the spirit of why we even have this binary operation called convolution, I want us to consider this particular question here, or this particular initial value problem. So if we were to just go along and say, well, hey, I want to solve this and I want to use Laplace transforms, okay? So of course, we'll take the Laplace transform of the left side, take the Laplace transform of the right side. And so if we do that, then of course, we know on the left side, we could split this up into Laplace transform of the difference of both of these, where this constant here is on the outside. And of course, we'll just take the Laplace transform of t squared. Now, if you recall, the Laplace transform of the derivative of a function is just s times big Y of s minus y of 0, okay? And of course, the Laplace transform of y is just y of s. So if we put that all here, we see that the left side ends up being what you see there. And of course, our initial condition here is y of 0 is 0. So we replace all that with 0. Similarly, we know that the Laplace transform of t squared is in general, or t raised to the n, I'll put it like that, in general is going to be n factorial over s raised to the n plus 1. And of course, if n is 2, then that ends up being 2 factorial over s raised to the 2 plus 1. If, of course, and I'll go ahead and substitute this in, if that's 2. That's plus, that's 2. So, of course, this is going to end up just being 2s cubed, because we know 2 factorial is just the same as 2 times 1, which is just 2. So we do all that. And we notice here we have common terms of y of s, so we factor that out. And we just have s minus 5 times big Y of s on the left side, 2 divided by s cubed on the right. And we divide both sides here by s minus 5. And we get this situation here. And of course, we could write it this way, or we could write it as a product of 2 rational functions, okay? So at this point, if we were solving this via Laplace transform, we would probably want to go the route of doing partial fraction expansion, okay? And that basically means we're going to rewrite this rational function as a sum of these 4 different terms here. And we do that because with partial fraction expansion, whenever we have repeated roots, we know that since this s cubed is like s minus 0 cubed here in the denominator, this is a linear expression. So the constant that we have to have here has to be 1 order less. So if this is of order 1, then that means that this has to be of order 0. And anything raised to 0 is just 1. So that's why we just leave it as a constant. And so we have to do that for everything from the lowest non-zero order, which is 1, on up to whatever the order is, which is 3 for this one. And then, of course, we do 1 for denominator of s minus 5. And so we go through the whole steps of being able to find all of these constants here. And in doing this, since we have this particular, now circle it right quick, since we have this way of being able to interpret y of s, we have an s cubed and an s minus 5 explicitly shown here in the denominator. So that means we would solve for c and d first, and then take this result and then subtract both sides by it, and then rearrange everything over here and eventually find out what this is going to be. And once we take these two terms, subtract both sides by it, put it over here and rearrange, we could either do the cover-up method again, or we could try to form this into one quotient and figure out what is my A and what my B is going to look like in that case. Okay. And so I just kind of go through those steps here, saying we use the cover-up method for C and D, rewrite everything to solve for what this is going to end up being. And from that, we determine A and B however we like. Okay. Now, the point that I'm trying to get at here is that even though that is a relatively easy problem to do in Laplace transforms, it still may take a while. Okay. And so the question is what if there was a way to directly solve for the solution of y of t versus going through all the steps that I just described in 1 through 3. And of course, in doing all these steps, I would still, even after doing all these 3 steps, I would still have to take the inverse Laplace transform of all 4 terms once I'm done. So once I find what, in this case, what A, B, C, and D are, I still have to take the inverse Laplace transform in order to get my answer, and then, possibly combine like terms. Okay. So if we did that, what would that actually look like? Well, let's see. Well, we know since big Y of s, which is the Laplace transform of our actual solution to the equation, can be written in this way here, let us make x of s equal this particular rational expression, and let's let h of s equal the other. So that now we have y of s is equal to x of s times h of s. Okay. Now I'm using this setup here because once we get towards the end of talking about convolution and we see how it's used to solve ordinary differential equations, you'll see that this is a desired setup for that to apply the theorems that we're going to apply. So we have this setup here where big Y of s is equal to the product of big X and big H. Then naturally, you would probably think here that, hey, if big Y equals big X times big H, then that must imply, if I do the inverse Laplace transform, that little y is equal to little x times little h. Okay. And so, of course, that would be something that you would naturally think, hey, that should work, right? And again, ignoring the fact that this is a Laplace transform, which is the form of an integral transform, we just look at the symbols and say, yep, that makes a lot of sense. So unfortunately, though, that doesn't work that way. And the method would not work because if we did what we just suggested, we would get the following. Okay. So if we did just like what we said here, remember this is big X of s, big H of s. And if we take the inverse Laplace transform of each of these, we got t squared for the first factor and e raised to the 5t for the second one. Okay. And so now if we take this equation, or take this solution rather, and plug it back into our ordinary differential equation, and so you see I've done that here. Once we do all the work for it, you see that we end up getting this statement here, okay? And this is a false statement for t being all real numbers, okay? The only time when this is true is when t is equal to 0. And of course, if this is going to be an identity here, then it means that this has to equal to the same thing as it does on the right side for all values of t in the domain of our solution, okay? And so, you see, that's not going to work. So we have to find another way to approach this, okay? Now, the reason why this didn't work is because, remember I said that the Laplace transform is an integral transform. And so what we essentially did is we took the Laplace transform, we assumed that the Laplace transform of our solution could be expressed as a Laplace transform of the product of these two functions here. And remember, by definition, Laplace transform is the improper integral from 0 to infinity of e raised to the negative st times whatever that function is, which is the product of these two. And what we did is we assumed that the integral of e raised to the negative st times the product of two functions could just be rewritten this way. And of course, we know from first year calculus that it doesn't work that way, okay? We also see this in second year calculus. This doesn't work that way as well, but this does not follow our integration properties. So because of that, we're like, yeah, not going to work. We're going to need to think of something else, okay? So the big idea here is, what if there was a way for us to redefine what multiplication meant, okay? Meaning, is there another way that I could define multiplication in between two functions, or two numbers in this case, in what I call the t domain? And so I'm only saying that because we're dealing with, let's say, f of t or y of t. This is what we're trying to find out. So if there's a way for us to redefine multiplication such that, in such a way to where the product of little x of t and h of t using this alternative multiplication operation would actually yield the product of the Laplace transform of both of those, okay? So essentially what I'm trying to say is this. So if I had x of t, and then there is some operation I come up with, and then there's another one, h of t, if I took the Laplace transform of that after I figure out whatever operation this is, what would I have to define this to be in order for this result to be this, okay? So put another way, how does regular multiplication in the Laplace transform domain translate to multiplication in the t domain, okay? So if we move on here, if we could find a way to redefine multiplication in this fashion, we would possibly be able to find y of t directly from just knowing what x of t and h of t are from performing inverse Laplace transform operations on big X and big H, okay? So all that's saying is that if I could find, and I'll just go back up here, if I could find some operation to make this actually true, then all I would have to do is take the inverse Laplace transform of this, inverse Laplace transform of that, and that would tell me exactly what my solution is going to be, provided that I know what this operation is, okay? So there is good news, and that good news is that it turns out that we do have such an operation, and that operation is called convolution, and that's why you're probably watching this video. Now, the secret to being able to define this new multiplication in a way to where it's actually going to work is that convolution is going to be defined as an integral transformation, somewhat similar to what the Laplace transform is defined as. And remember, the Laplace transform is itself an integral transformation. So now what I'm going to do is state the definition of convolution. I'm going to work through some simple examples using this new binary operation that we're going to define, and then discuss some basic properties we need to be aware of as we use this new operation, okay? So this first video will stop at this point, okay? The second video in the series will start here, where we will finally show how this operation can be used to solve ordinary differential equations by revisiting some of the examples that we did whenever I talked about the Laplace transform and the Laplace transform videos that I made. So if you haven't checked out the Laplace transform videos and you need to, then I'll probably say go ahead and do that. If you're already familiar with Laplace transform, then you can just kind of take the examples as is and we can work with them from there, because we'll still kind of work them from scratch for this particular concept. So the definition of convolution is, we say let f and g of t, for both of those, be two functions that are defined on some interval from 0 to infinity, where the functions are defined at 0. Then we say that the convolution of the two functions f and g, or put another way, we convolve f and g, you could say it that way as well, is denoted by this notation here. And this is just a notation when we don't explicitly say what variable these functions are defined with respect to. When we want to explicitly say what variable these functions are defined with respect to, we can write it like this. You will probably see it written more so like this. I personally don't like this notation, only because whenever you look at it this way, it doesn't let you know, well, if g is defined in terms of t, what is f defined in terms as, okay? And so even though it's written like this, they really mean this, okay? And this is following the same kind of notation that you would if you were doing a composition of two functions, okay? So if you remember this notation with the little open circle, of course, we also would notate this way. But one thing that we wouldn't do is do this, okay? And so the way that this operation is kind of working is the same way this one is. So that's why it's, in my opinion, good practice to put the parentheses around it, okay? So, and of course, we also have this notation as well, where you're explicitly saying what variables each function is defined with respect to. So main thing here to notice is that you have this new multiplication defined in terms of regular multiplication of your function times the other function with some kind of horizontal shift in it. And really, this is a horizontal shift and reflection across the x-axis. And I say that because remember, t is a constant here. Since we're taking an integral with respect to x, any other variable that does not have, that is not x, is a constant. And so this t minus x here is actually minus x minus t. And if we remember from pre-cal, we know that variable minus positive number here is going to be a horizontal shift to the right, t units in this case. And then this minus on the outside here means that we're doing a reflection about the y-axis here, okay? So that's why I say that here this function is really a horizontal shift and a reflection about the y-axis there. So in this case, we have the multiplication of these two functions, and we're going to take the integral of that. And that is our newly defined operation that's called convolution. And again, I know you've heard me say this. I've called it a binary operation because we need two things in order for it to make sense. So just like addition is a binary operation because 2 plus 3 is equal to 5, we know that we have to have 2 plus something in order to get a value here. We need the same thing for convolution. Of course, if I said 2 plus and then I just left that blank, you would say 2 plus what, right? So in the same sense, we just can't say f convolved with blank. We would say f convolved with what, okay? And so that's why I'm calling it a binary operation. So now that we know how this is defined, I'm going to erase some of this and then we're going to step through this example. All right, so for our first example here, we want to convolve both f and g, and both of these functions are defined in terms of x. And we say that f of x is e raised to the 3x, g of x is e raised to the 5x. So in doing this, recognize that, and I'll write this here so that you can, well, I'll do it here. This may be a little better. Write it like this. So notice that whatever your variable is for the function that you're trying to convolve, that's going to be the same variable constant that you're going to put in the upper limits of integration here, okay? So here, since both of these functions are defined in terms of x, then this is going to be my variable constant, as I'll call it. And here, I'll come up with another variable. I'm using t. If you look at some other resources, they may use tau or something else, but I'm just going to use t here. And so that means that t is a variable to the integral. T is a variable to the integral. X is a constant, okay? Now, whenever we apply this, note that what f of t says is wherever you see go here. So wherever you see x for f, you're going to replace it with a t, okay? So here we're going to replace x with just t. Same deal here. Wherever we see x here, we're going to replace it with x minus t. So here, in place of x, we have x minus t. And so that's why you see that whenever we plug this into the formula for convolution, it looks this way. Now, the thing that we like here is that if I was to take this 5 and distribute it to both terms here, then of course, all of this would just be e raised to the 5x minus 5t. And so in looking at that, if we use our properties for exponential expressions, we know that we could rewrite this as e raised to the 5x times e raised to the negative 5t, which is here. And notice that t is the variable, so that means x in this case is going to be the constant. So e raised to the 5x, all of that is a constant, okay? So since it's all a constant, I could literally factor that out of my integral and deal with what's left. So if we do that, then of course we take the e raised to the 5x out, combine what's left, and of course using our exponential rules here, we can just add the exponents. And then at this point, this is just basic cal A. We take the antiderivative of e raised to the negative 2t. We use substitution rule, and we're going to get e raised to the negative 2t divided by 2. And then using the net change theorem, we plug in x everywhere where we see t first, minus plug in 0 everywhere where we see t. And of course, for the second term, that ends up being 1. And then we just combine what's left, do some simplification, and we see that e to the 3x convolved with e to the 5x is just going to be 1/2 of the difference of e raised to the 5x minus e raised to the 3x. And so if we were to multiply e raised to the 3x and e raised to the 5x in a convolving fashion, this is what it would end up being, okay? All right, so let's look at another example so that we can see how do we convolve functions that are a little bit more complex than these basic exponentials. So let's let f of t equal sine t and g of t equal e raised to the negative 2t, okay? And so what we want to do is convolve these two together, where we're specifically saying let sine be the f and e raised to the negative 2t be the g, okay? Now you're probably wondering, well, could I actually flip these around, okay? And you actually can, okay? And we're going to address that more towards the end of this video when we start to talk about the properties of convolution. For right now, we're just going to keep it simple and do these examples as is. However, I will say this. The reason why this problem was chosen this way is because notice that we have this horizontal shift and reflection across the x-axis. And if this was the function that I needed to actually go in and rewrite this as sine of t minus x, now I've just made my problem more difficult because now I have to remember the addition formulas for sine of the difference in between two angles, okay? Versus if I let this be the function where I do this horizontal shift and reflection across the x-axis, reflection across the y-axis rather, then in this case, that's kind of like the first example where I just have, e raised to the something x, and I can factor it out, and life is easy, okay? And so that's what we're actually going to see here. So let me erase this, and then we'll get going with this problem. So we convolve f and g together. Just write sine of x here, and everywhere where I see t here, I'm going to replace it with t minus x here. And then, of course, I can distribute the negative 2 to both terms there, and then rewrite that as the product of two different exponential expressions. Of course, since x is going to be the variable now, then t and e raised to the negative 2t is going to be the constant term now, okay? Now, I'm going to stop here to make sure that you get what's going on, because if we go back to the previous example, notice that I wrote this different, okay? Notice that x was my constant, even though it's a variable, it's acting as a constant in this integral, okay? And my variables here were t, okay? And so I did this on purpose so that you don't necessarily get married to having the same kind of notation every single time. I want you to understand more so of the placement of things. So whatever variable that you have here is going to act like a constant in this integral, and it's going to be the same thing that what you're trying to convolve is going to be defined as, okay? And of course, whatever your variable here is going to be different from this. So that's the main thing that I'm trying to get at. And it really doesn't matter what symbol you use as long as you make that distinction. So here we see that these two match, which they're supposed to, and this should be different. The x here should be different than that. So we know all that matches. All right, so moving on, we go ahead and factor out the e raised to the negative 2t, and we see we need to integrate sine of x times e raised to the 2x. And so in taking the antiderivative of that, we notice that that's one of these, what I like to call circular integrals, where we can do integration by parts, but we're going to have to do it at multiple amount of times for us to be able to find out what it is. So I'm going to use augmented tabular integration by parts here, which basically says I'm going to select my e raised to the 2x here to be my u, and my sine of x dx to be my v, since I'm going to rewrite all of this as just u times dv. I take successive derivatives of u and take successive antiderivatives of dv until I can look across and see that I can recover the main thing I was trying to find in the first place. Okay, so we see how that matches the product of this and that, ignoring the 4 here. So we know here we can kind of look across, and the formula would just be, we just go diagonally across. So this times this minus that times that plus this times that. And so that's basically what this formula is saying here. And then from there, we just put it all together. So we know that the integral that we're trying to find, which is integral from 0 to t of sine x times e raised to 2x dx, ignoring this part right now, we know that that's just going to be whatever this tabular integration tells me. So first 2 terms here, diagonally across, is what this is. Second 2 here. And of course, this subtraction and that negative make this a positive. And we know from the normal, let me redo it here. So from the normal formula for integration by parts, this is what we have. And of course, this portion, whenever you have limits of integration, they go from a to b. So that's what I'm doing here. And so now we have plus, and then the augmented part here is once we find out, looking across, we can recover what I was originally looking for. I can just write this as a definite integral in this case. And of course, I want to get the integral and all of this to look similar to what I have here. So we notice here we have a minus 4. I can make that same as subtraction and plus. And what I could do is just basically take this term and add it to both sides here. Okay. Now I'll just say 4 times all that. So if I have one of these plus 4 more of these, then I'm going to end up having 5 of these. And of course, everything else is just what this is evaluated at t, everywhere where you see x, and then minus the same thing at 0. And so that's what this step is. From there, we see that our first 2 terms, just what we normally saw, but instead of having x, it has t. Second term, everything pretty much reduces to either 0 or 1. And at that point, what we want to do to get this 0 to t, integral 0 to t, e raised to the 2x times sine of x dx by itself, is we are going to divide both sides by this constant 5 here. Okay, so if we do that, of course, here we divide by 5, and here all that divide by 5, and so you'll see that we'll have 1/5 times this term, 2/5 times this term here, and of course, minus a negative is the same as addition. We basically got 1 here, so that's where the plus 1/5 comes from. Okay. So now to finish up, now that we have this expression here, all that we're going to do to get the final integral here is multiply by e raised to the negative 2t, which basically means we're going to distribute this to all 3 terms. And if you notice here, anytime you have e raised to the 2t with e raised to the negative 2t, that ends up being e raised to the 0, which is just 1. Okay, and we see that happens for both of our first two terms. And then, of course, for the second term, it's just 1/5 e raised to the negative 2t. And so our result actually ends up being that f convolved with g is actually going to be all of this. Okay. All right, so I have 2 more examples of this, and I'm not going to spend as long going through them because now that we've kind of seen a few examples, we can kind of go through this a little bit faster. So again, we want to convolve f and g together. So in this case, I'm using z as my variable for the integral. So of course, t here matches t's that are here. So we know we're good to go. Everywhere where we see t here, replace it with z for f. And then everywhere where we see t here, replace it with t minus z. So we do that. And then of course, here I'll go ahead and FOIL this out. So once I FOIL it out, then I distribute the z raised to the negative 1/2 to both terms. And then from there, just try to simplify. Okay. So I decided to split this up into 3 separate integrals. And notice here that t, sorry, not t, but z is going to be my integral of integration. So it looks like I have written that incorrectly here. So let me go ahead and fix that. So yeah, somehow from here to here, I didn't copy that right. So this should be z, that should be z, 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 z. And of course, I'll keep doing it here. So z is our variable of integration here. And so with z being that lets us know here that 2t is going to look like a constant to this integral. And here t squared is going to look like a constant to this integral. So that's why that gets factored out. And then from there, I just take the antiderivative of all 3 of these terms here, which is relatively simple to do. Use net change theorem to plug in t everywhere where I see z, minus, same thing with 0 for each one of these. And then I just simplify my answer. And I notice that once I do all that, simplify everything, all 3 of these terms are like terms. So all I have to do is just add them together, and I get 16/15 times t raised to the 5/2. And that is what f convolved with g is. Okay, so let's work on our last example of convolving 2 functions together before we look at some basic properties of convolution. So we want to convolve cosine and cosine together in this case. And so what that would mean for us here is, again, we would have cosine of t being our f of x function, or sorry, f of t function rather. And we would have cosine of t of x minus t for the other, okay? And again, note that the variable here, which is we're translated as a constant inside the integral, is the same as what each of these functions are defined as. And what this is should be different than what the variable here should be different than the letter here, okay? So we see that we're going to have to do the product of 2 cosine functions at different arguments. And so we know that we have the product to sum formula that we could use to be able to rewrite this in a way so that we can actually take the the integral of it relatively simple. Okay, and so here we know that the product to sum is just going to be 1/2 of cosine of a plus b plus cosine of a minus b, where I'm letting my t here be a and I'm letting my x minus t here be b. And so if I go ahead and substitute all that in, we see that in terms of what we're talking about here, this will be our result. Okay, Now, just as a side note, if you're wondering, well, I'm on a test and I'm not going to remember to do that. Of course, one way to do it is to memorize it. Another way that I would say is just memorize a few things and leverage that. So one of the things I definitely think you should memorize are all of the trig addition formulas, mainly the sine and the cosine. Okay. So for this demonstration, we could just say cosine of a plus b. That's just going to be cosine a cosine b minus sine a sine b. And then, of course, cosine of a minus b. Everything else will pretty much be the same, except for now the sign is going to be plus instead of minus. And so here, how we actually get the product of some formulas here is that notice we have products of functions here, okay? And so here, if I was to add these two, if I actually did that, these would cancel to 0, and I have two of the same thing here. And then, of course, I have cosine of a plus b plus cosine of a minus b. And then, of course, if I divide both sides by 2, that reduces to 1. And, of course, now I have cosine of a times cosine of b is just 1/2 of cosine a plus b plus cosine a minus b. So that's literally what I did when I wrote that out, because I normally don't use formulas or anything like that and just reference. I'll just say, well, hey, this is what it is. And I do that just to kind of keep my mind fresh with it. So once we actually know that, then we can actually plug that in, and then life is pretty easy at this point. So we know that this is going to be a two-term function here. And notice that since my variable here is different than it is here, cosine of x to this integral with respect to t is going to look like a constant, okay? For this term, know that this is acting as a constant term, and this is actually going to be the term that's connected to this variable here. So we know that whenever we take the antiderivative of a constant, it's just that constant times the variable here, which in this case is going to be t. And when we take the antiderivative of cosine of 2 times t minus a constant, it's just going to be sine of 2t minus a constant, all that divided by 2, using the substitution rule. And then, of course, we'll evaluate that from the number 0 to the number x, okay? Where x here again is considered to be a constant. So I plug in x everywhere where I see t. And that's why I get that here, and I plug in 0 everywhere where I see t here as well. So I'll plug in 0 here, plug in 0 there. And so this is how I end up just getting x times cosine of x plus 1/2 of sine x plus sine x all on the inside, okay? And then, of course, from there, it's just a matter of distributing the 1/2 through, and then just simplifying as much as you can, and this is what we get. And so we see that cosine convolved with cosine actually gives us a sum of sine and x times cosine functions, okay? All right, so let's move on over and talk about some basic properties that we need to recognize as we're using this new operation that we've developed called convolution. All right, so now that we kind of know what this new operation is, one of the things that we need to know is what can we do with it, okay? So just to kind of make my point here, let's go back to first year calculus. Let's say we talked about derivatives of some function, right? And so one of the things we said is, well, what happens whenever I take the sum of two functions and I want to take the derivative of that. Okay. Well, we just said, guess what? Just take the derivative of each of them separately and add it together. We said the same thing with subtraction. Okay. We said for derivatives, how do we deal with taking the derivative of the product of two functions? Okay. And notice that what we came up with is we take the derivative of the first times the second plus the first times derivative of the second. And notice that this did not equal derivative of the first times derivative of the second. Okay. It did not equal that. So when we were doing derivatives, we saw that what we would naturally want to think that it is would not work. Okay. So my point in saying all this is I can run through more rules, but my point in saying all this is that every time we introduce a new operation or a new operator, like in the case of the derivative, because that is an operator, one of the things that we want to know is what can we do with it? The main things we're trying to figure out is how do we add with it? How do we subtract? If it makes sense, how do we multiply? How do we divide? And we want to know other things like, all right, well, what is this particular operation or operator commutative? Okay. And so commutative just basically means does 2 plus 3 equal 3 plus 2? Okay. Associative, we want to know that too. So we want to know if I say 1 plus 2 plus 3, and I group these two together and add it, is it going to be the same thing as me saying 1 plus 2 plus 3, and I group these two together, and then I add the one afterwards. So I want to know, is it commutative? Is it associative? Okay. And so I also want to know, is it going to be distributive? Okay. So if I have 1 times 2 plus 3, is that going to be equal to 1 times 2 plus 1 times 3? And will it also happen the other way? Well, if I come and do it like this, well, I still get 2 times 1 plus 3 times 1. And will these two be the same? Okay. Now, if we have operations that are commutative like this, well, let's say commutative in multiplication, I'll change this and say 2 times 3 is the same as 2 times 6. Then here, we know that any two numbers that are multiplied, 2 times 3, same as 3 times 2. So that works. So my point here is that we want to know, does this new operation that we're calling convolution have these properties? Okay. So I call it in my notes here, we want to find out the flexibility of this particular operation by knowing its properties. And like I've said before, we want to know, is it commutative, associative, distributive? We also want to know things like what elements of f can be used with this operation to yield 0. So in other words, if I have some function f and I convolve it with that, is this going to actually be 0? Okay. Or is it going to end up being something else? Okay. Also want to know, if I take that same function and convolve it, what do I have to always make it equal to itself? So we know with regular multiplication, let's say here, if I had some number times 1, that's going to be equal to itself. So we're wondering, do we have this same sort of thing going on here? Okay. And so if we don't have this, then we want to know, all right, well, what's the difference in between this and what this would look like? So it turns out that all these properties I've stated, convolution does have something that makes some sense or looks something similar to what we're used to seeing for that. And so I'm going to state all of these, but I'm not going to prove them. I'm just going to state them. And then we're going to use this information to help us in our second video to eventually solve ordinary differential equations with it by using that in conjunction with the Laplace transform. Okay. So one thing that we know is that we could take a constant multiple of some function and convolve it with another function, and doesn't matter where that constant multiple lies, either if it's with f or g, we can still factor it out. And of course, this is true because remember that this in general is an integral, and we can factor out any constant out of an integral. Okay? Now, we also see here that f convolved with g is the same as g convolved with f. Okay? So we know that this is going to be commutative. Now, I'm actually going to go into detail on this one so you can see why that is, because this is like one of the more important ones. So associative, we know that it follows that property. So anytime we want to convolve two functions together, then convolve a third, it doesn't matter the order in which we do it. We also know that distributive property from the left and distributive property from the right will both basically end up equaling the same thing, provided that we have all the same numbers here. Again, I wrote this a little bit differently so that we could look at it differently. But again, what's happening here is a little bit different than what's happening here. But what we are saying is that if we want to distribute to the right, that's fine. If we want to distribute to the left, that's fine. So distributive, we want to distribute convolution over addition. So it works both ways. Now, you're probably wondering, well, why is it that all of this is important? And that mathematically, we don't take these sort of things for granted. Okay. So for instance, if any of you have studied matrices, you'll know that matrices are not necessarily commutative. Okay. So a matrix A times B is not necessarily equal to a matrix B times A. So we know that. We also know because of that, matrices are not distributive. Okay. And so whenever we deal with matrix algebra, there's a bunch of things that we have to do totally different because of the fact that we don't have the commutative property and associative property working the same way as it would in regular multiplication. So this is part of the reason why we wanted to check this out, because if we had defined this operation and let's say it wasn't commutative or associative like how we thought, we were like, well, we can use it, but let's try to find something that's a little bit easier to use. And what easy is saying, all right, well, I have something that's going to be commutative. I got something that's associative, and I got something that's distributive that works very similar to how it works with regular multiplication with numbers. Okay. So that's kind of what we were looking for, and that's what convolution actually does for us. So other properties, we see that if I was to convolve some function g with the number 0, or if you want to translate it as a function y equals 0, we see that we'll get 0 as a result of that. And this is simply because 0 times anything is 0. And if we take the antiderivative of 0, that's just going to be some constant evaluated over 0 to t. Doesn't matter what this is, because net change theorem says that we have constant minus a constant, which is 0. Okay. So we see that if I convolve f with 1, or what's popularly known as the identity element for regular multiplication, we know that convolution is commutative, but notice here that f here looks like an integral there. So if I convolve f with 1, it's not going to come out to be the exact same thing that f is. Okay. Only time that would probably be maybe in special cases is if f is like e to the x or something like that. Okay. Now, this one, it says that if we convolve two functions and we evaluate it at 0, doesn't matter what those two functions are, I'm always going to get 0 as an output. And so that's partly because of what we see here. And we know from first year calculus that the 0 with property for integrals basically says if you do a definite integral from limit to another limit and those are the same, then you have a 0 with, so you can't take area on the curve. So it's effectively 0. Okay. All right, so before we get into this last thing about the notes on actually evaluating whenever we convolve f and g, I am going to go ahead and show you over here how we, for this one, why this is actually commutative. All right, so I see over here I have f convolved with g, and we know by definition that equals this. So what I want to do now is I would like to switch this to where I could possibly make it be like this, which means that my g would be in this spot and my f would be in this spot. Okay. Now to do that, one of the things I can do here is do substitution for this. Okay. So let's let, I'm just going to say u equal t minus x. And so if I do that, then of course I could rewrite this so that I could actually solve for t. Let's see, this x plus u is equal to t. And so from here, what we would want to do is go ahead and solve for x. And so the reason why we want to go ahead and do this is because, remember, we're trying to change the way that this is going to look. So I want this to look like g of single variable here. Okay. And I want whatever this is to look like this times the, I guess the horizontal shift and the reflection across the x-axis. So we have this situation here. So now that I have this, I know that I can do dx over dt. Yep, sorry about that. That should be du, not dt. And so if I take the derivative of x with respect to u, then of course t is acting like a constant. So that just goes to 0. And the derivative of minus u is just going to be minus 1. So this is going to be dx is minus du. Okay. So once we have all that, I can just go in and substitute everything that I have here. Now, I can also do my limits of integration here, but I'm going to wait to do that until a little bit later. All right, so do my integral here. I know that my x is the same as t minus u, so I'm going to have f of t minus u times. And here I know that t minus x is just going to be u. Let's try to get that acting right here. Come on. Yeah, okay. All right. And so then my dx is going to be a minus 1 times du. Okay. So now to translate what these limits of integration are going to be, this would literally be u of 0, and we would have u of t here. Okay. And if we were to work on that down here, then u of 0. So knowing that x is going to be our variable and t is our constant, that's just going to be t minus 0, which is t. And then after that, we would have u of t, and this would just be t minus t, which is 0. Okay. And so what this basically means here is that we would have a t here and a 0 there. So I'll go ahead and replace that. And so now we have, what is this? U of 0 is going to be t, and u of t is going to be 0. But notice that we have the -1 right here, which we know that says that we need to flip these. And so now, once we flip it, we see that we have this in the form of what we are looking for. And of course, since multiplication generally, how we normally know it is commutative, we could rewrite it this way. And of course, by definition, this means that G is convolved with F. And so you'll see here that F convolved with G is the same as G convolved with F. It's just a matter of what function do you want to do this horizontal shift and reflection across the y-axis with. And so we'll see whatever function we do this with would actually, we need to be very careful on how we select that, because it's going to help us to be able to make life easier if we select it right. Okay. All right. So let's go back and wrap this up now. All right. So the very last thing that I want to talk about is how do we actually evaluate the convolution of two functions at a specific value of t. Okay. So we need to know how to do this correctly here. So if we look at a problem that we did earlier, which is we want to convolve e raised to the 3x and e raised to the 5x, recall that we had to go through the whole thing of doing integration to finally get this. Okay. Now, part of the reason why I like putting the parentheses around the two functions that we're convolving is because, at least to me in my mind, it helps me to remember what operation to do first. Okay. So for instance, if we had, let's see, the composition of two functions here, we know that if we were actually doing this, one way that I could actually evaluate this is to actually figure out what the composition of f and g is. And then after I get that answer, then I plug in my value of x, whatever that's going to be, into it. Okay. So I could do that. When we're convolving, there's a whole lot more going on than what we're doing here, because I'm pretty sure you all are familiar with the fact that another way that we could actually do this is we could plug in whatever value of x we have in the g, and then after that figure out what g is, and then plug it into plug that result into f, figure out what that is. Well, a convolution is not going to actually work that way. So we actually have to figure out what all this is first and then plug in our value. So I want to show you what the incorrect way looks like versus the correct way looks like, so that you'll know the difference. So the incorrect way just basically says that, hey, we're going to blindly just plug in -2 into here and here before we even start convolving. Of course, and if we do that, you'll see that you get these two constant values, and then now you're convolving two constant values. And so integral of any constant is just that constant times variable t, evaluated from 0 to x, where x is assumed to be a constant for the integral. And you see that you end up with this particular situation here. Okay. And this is incorrect. So, and notice that this form does not mimic the form that we had here in any shape, form, or fashion. So that's another reason why we know it's not correct. Okay. But if we go and do it the correct way, then of course we actually have to figure out what all this is first, which means we got to actually do the integration here. And of course, we've already figured out that this is what that is. And it's at this point that we now say, well, hey, let's plug in -2 everywhere where we see x. And then we see what the final answer is here. And again, we notice here how the profile of this answer, even though it is a constant and it's an ugly one at that, it does mimic what this looks like. And that's kind of what we're looking for there. So just want to make sure that you know that if you're asked to convolve two functions and evaluate that result at a particular value of x or t or whatever, that you do that correctly. Okay. All right. So this concludes the first video in this video series on convolution. The next video, which will be the final one, is we will go over how we use the Laplace transform and this new binary operation of convolution to be able to solve ordinary differential equations. I'll see you there.